So what I'm going to talk about is a topic that's been touched on by some of the earlier speakers in this workshop on trying to leverage some of the things that we know about machine learning in the context of solving different inverse problems in imaging. So in particular, the kinds of inverse problems that we're interested are often kind of classical. Things like inpainting or filling in missing pixels, deblurring, superresolution, compressed sensing, MRI, radar, etc. And in general, we can formulate it like this. There's an image that we're interested in, and in vectorized form, we would call that beta. And we don't get to observe beta directly, but rather we observe some linear projections of it, x beta, plus a little bit of noise, and that's y. And so ultimately what we want to do is to recover beta from these observations, and I've just got a couple of little examples up here. So this is a very well-studied problem in the image processing literature, and of course classical approaches go back to the 1940s. So Tikhonov regularization stemmed from the observation that simple least squares solutions to this problem would work well if we had no noise, but as soon as you add a little bit of noise, if your inverse problem is ill-posed, then you just become super sensitive to that noise and you can get terrible results. And so they said, okay, well, let's add a little bit of regularization, and in particular, you could say, well, let me just try to make sure, okay. You could try to make sure that the norm of beta is not too big, and there's a nice closed form solution to this that gives us much better looking results. Now, since the 1940s, people have tried to build upon this idea of trying to leverage different kinds of structure in images in order to better solve these kinds of inverse problems. So things like total variation or exploiting sparsity in some basis, such as a wavelet basis or other kinds of dictionaries, or even using models of patches in the image lying on subspaces or different kinds of manifolds. We've considered all of these, and I think we can think of all of these methods as somehow modeling the geometry or the structure in the image based on some sort of heuristic or intuition or understanding of image geometry. Okay, so in general, we could think about it like this. We've got some observation y, and what we are going to do is we're going to try to estimate beta by perhaps solving an optimization problem where we try to minimize a measure of error, such as squared error, plus some regularizer. And the question is, what should this regularizer be? So we're kind of having multiple stages of enlightenment here, where we started with classical methods like Tikhonov regularization. We've built upon that to build more sophisticated prior knowledge of image geometry and structure into regularizers. And now the question is, can we do something above and beyond that by leveraging the vast quantities of training data that we have available and have been used so successfully for things like image classification and computer vision? Okay, and there's a ton of potential here. So just as one example, here's an inpainting problem where we want to fill in the guy's face. And if you just use standard kind of like wavelet sparsity methods, then this is about as well as you can do. But by leveraging training data, we can just do significantly better. Okay, so because of this potential, many people have been looking at this problem. Here's a subset of the works on that topic. And we've heard some more about it today. So in general, I think that we can think about these methods as falling into four broad categories. So the first category is model agnostic. So we've got y's, which are observations, we have betas, which are desired images, and we might try to use training data to learn a mapping from y to beta that completely ignores x. So this would be like a blind deconvolution problem where we don't know anything about what our image has been convolved with. And these methods are okay as long as the inverse problem is pretty well conditioned. So if this x operator looks pretty close to an identity matrix, then we're in good shape, but sometimes they can struggle in more complicated inverse problem settings. Okay, the next category, which I'm going to talk about in a little bit, is decoupled. So they separate out the task of leveraging the training data and doing some kind of machine learning from the task of solving the inverse problem. So they decouple these two things. I'm going to explain exactly what I mean by that in a second. And then there's unrolled optimization kinds of techniques, and Emily did a great job talking about some of those earlier today. And then finally, I'm going to talk about sort of a fourth approach that we've been working on called Neumann networks. Okay, so first of all, let me talk about these decoupled approaches. So for the moment, imagine that we knew what regularizer R we cared about. Then you might try to solve this optimization problem by using, well, known tools. So in this slide, for instance, I'm showing a proximal gradient algorithm. And essentially, you start with some initial estimate, beta hat 1, and a step size eta. And you alternate between two different steps. So in the first step, you do gradient descent relative to your loss function or your data fit term. And in the second step, you apply your regularizer through what's called a proximal operator, which again, Emily talked about earlier. But you can think about this as roughly like a denoising operation. So for instance, if this regularization function was sparsity, the L1 norm, then this proximal operator would amount to doing some soft thresholding or denoising the Z, the result of the gradient descent. And so what people said was, well, okay, then if what we're ultimately doing, at least on a high level, is alternating between gradient descent and denoising, and gradient descent denoising, then why don't we use our training data to just learn how to do the denoising without explicitly writing down a nice closed form expression for the regularization function. So let's just replace this whole proximal operator with something like a learned neural network. So this is decoupled because the way people would work with this sort of construct is they would say, okay, let me use all of my training data and learn how to do denoising, learn that network, and then after I've done this, then I can go back to my proximal gradient algorithm and just plug in this learned denoising scheme. So I'm not using any information about X or my inverse problem when I'm doing my training of my network. They're kept very separate. Okay. Another example of this decoupled approach leverages GANs, which Camille did a nice job explaining just now. So the idea would be that we're going to think about all the images that we care about as somehow lying on some sort of manifold. And that manifold, we don't know directly, but we have samples drawn from that manifold, and that's our training data. And so we could, if we knew that manifold, we would do something very natural. We would say, okay, if our image, our candidate image is on the manifold and it's a good fit to the data, then great. And if it's not on the manifold, then we should keep looking for something better. So you would have a regularizer that gives 0 penalty to images on the manifold and a big, giant penalty to anything off the manifold. Okay, and so then hopefully you can hone in on images you care about, like cats. Okay, so how would this work? Well, the idea is that you would learn some sort of generator that would somehow map a vector Z in a low-dimensional space to an image on this manifold. And so if you've got a generative function G like that, then you can think about your regularizer as basically being 0 for any images in the range of that generator and infinity otherwise. And so if you know that generator, then you could say, now let me just choose whatever image beta is in the range of that function and is the best possible fit to my data. And again, this is decoupled because you would learn your generative model using your training data. Then once that's done, you stop and you say, okay, now I'm just going to plug it in to this thing in the bottom corner to solve my inverse problem. Okay, so here's an example of this in action when it was trained on the CEB data set with 80,000 different images, and it seems to work reasonably well. But if we were to redo this and only train with 2,000 images, it breaks down pretty quickly. In fact, it breaks down with training sets well above 2,000. So I think even at 50,000, we start having significant problems with these sort of decoupled methods. And this has caused a lot of concern and consternation, and some of the top thinkers in the US have even commented on how untrustworthy these results are. Okay, so what's going on here? Why do things start to break down like this? I think implicitly what's happening with these decoupled methods is that when we're doing the training, we're learning some sort of prior probability model or prior probability distribution for the space of images that we care about. So we could call that P of beta, this prior probability model. And then once we have that prior, then we can do things like map estimation. We can say, okay, let me try to find among all the images that fit my data, the one that's got the highest prior likelihood. Okay. But once we think about it like that, we can start to see why these methods have problems when you have smaller amounts of training data. So in particular, people have studied things like probability density estimation for a long time. And so if we had d-dimensional images, d-pixel images, and this probability distribution were to lie in something like a Bezov space with smoothness parameter alpha, then we can show is that the minimax rate for learning this probability distribution scales like n to the minus alpha over 2 alpha plus d. Okay, so what this means is that if I wanted to learn this prior probability distribution, P of beta, up to a certain amount of accuracy, then how many different training samples I need, n, is going to depend on how many pixels are in the images and how complicated this density function is. And these are minimax rates, which means that it's not like we're just using bad density estimation methods or that we need to be smarter about how we build neural networks. No learning method is going to be able to improve on this rate. Yeah?
Which type of space is it? With which P? Smoothness alpha and which P? You need some P.
Oh, I'm assuming L2 norms. Okay. Yeah, thanks. Right. So, I mean, maybe images aren't really in a Bezov space. Maybe the distribution is even more complicated than that. It probably is, but this is somehow a best case that we could hope for. And so what can we do instead to kind of sidestep this challenge? Well, again, what we're kind of doing is we're implicitly learning this probability distribution P of beta and then using it to solve the inverse problem after the fact. And the problem with this, oh yeah, Albert.
Just a question on your last slide.
Yeah.
So it's P, the P of beta, P would be the probability distribution of images. So it means D is really the dimension of the size of the image.
Right, D is the size of the image.
Okay, so you're talking of a terrible, okay.
Terrible.
You're not talking about the image itself as a function of two variables being in
no, that's right. I'm thinking about beta as being like a vector of d pixels, and it's lying in this d-dimensional space.
Now it's very pessimistic.
Yeah, it's very pessimistic, exactly. No, I'm glad you asked, and please don't hesitate to stop with other questions. Okay, so I like this inpainting example because I think it's a really good source of some intuition of what's going on here. So in particular, when I'm trying to fill in the missing pixels in this woman's face, there's all kinds of stuff going on in this image that's totally irrelevant to that task, right? What's going on in her eyes has no relevance, what's going on in the background has no relevance to what her eye shape is, right? So if I spend all my time trying to learn this full prior probability distribution, I'm going to spend a lot of effort trying to learn what's going on in the background or stuff that's irrelevant to the inverse problem at hand. And so what this suggests is that perhaps we could do better and sidestep this very pessimistic result by saying, instead of trying to learn the full prior density P of beta, maybe we should do something that's a little bit more oriented to our task at hand and learn the conditional density of the stuff we're missing given the stuff we observe, or a little bit more precisely, the orthogonal complement of x times beta given x times beta. Okay. So this can actually help quite a bit. There's been a lot of studies on conditional density estimation. So for instance, if the stuff that we're trying to infer, basically the null space of x, is only depends on a small number d prime of elements that we observe, then the minimax rate scales with d prime. And just to kind of give you a little picture here, is it showing up there? No. Oh, okay, here we go. So if I wanted to get, a 50% error, then I might need a relatively small number of training samples to achieve that error rate relative to the number of samples way out here that I would need if I wanted to learn the full prior probability distribution. Okay, and there are similar things that go on with smoothness. There's a lot of reasons to think that the full prior probability distribution over all images is not necessarily a smooth distribution, but these conditional densities could be far smoother. And again, the smoothness of these densities impacts what these learning rates are or how many training samples we need, and so we can potentially do much better. Okay, so what that suggests is the following. Like there's a lot of reasons to think that we should focus on, at least implicitly, the conditional density instead of the true density. And another way of thinking about that is that there's no way a decoupled method is going to be able to accomplish that. We should be thinking about our inverse problem or thinking about x right from the very beginning, because that's the only way we're going to really be estimating this conditional density. Okay, so those are decoupled methods. So the next kind of category that I mentioned were unrolled optimization methods. And these kinds of ideas date back several years, where people said, look, in general, if I wanted to solve an optimization problem like this, I might use some sort of iterative scheme where I start with some initial value and I apply some operation that somehow depends on x and r, and then I do it again and again. So I can think about this in terms of some kind of block diagram where my first block corresponds to one of these iterative maps. And then I do another block for another iteration, etc. So each block in this diagram corresponds to a different iteration in an iterative algorithm. Okay, so then what you could do is you could say, all right, given this framework, let's learn R from the training data, and we're going to consider it in the end. So we're going to take into account the fact that each one of these blocks depends on x. So unlike the decoupled approach, we're going to think about this system as a whole from the very beginning. Okay, so here's an example of what I mean. Let's imagine that our regularization function, R, is differentiable. So then what you might do to solve this optimization problem is simply do gradient descent, right? So you would say, all right, my estimate beta hat k plus 1 is my old estimate beta hat k plus a step in the negative gradient direction. And we can think about this in my little block diagram as this. So here I'm doing, I'm doing this gradient with respect to my squared error and my gradient with respect to r. And I'm adding, gradient with respect to my regularizer, and then I'm adding them up to get my new iterate. Okay, so there are variants of this. People have considered doing similar things with proximal gradient algorithms, interior point algorithms, primal dual algorithms, but the basic idea of unrolling hopefully is coming across, where people would start from this perspective and then say, all right, now let's take some component of this diagram that corresponds to the regularizer and replace that with a neural network that we're going to learn. Okay, so I've got this giant block diagram, and now what I want to do is I want to learn this neural network that corresponds to the gradient of my regularizer. And again, you would train this from end to end. So you would feed in some initial value that depends on your observation y, and you would get out a beta hat, and you would train this so that you were optimally, or solving this inverse problem as accurately as possible. Okay. So these unrolled optimization approaches are all based on optimization. And when we start using neural networks in here, a lot of the underlying theory, a lot of our underlying understanding of how these optimization algorithms work starts to break down. So for instance, we know what happens if our regularizer is convex. We can say all kinds of things about convergence, etc. But now if we've got a non-convex regularizer and we're only doing a fixed number of iterations, it's not really clear what kind of properties this thing is going to have. And so you can't just simply blindly muck around. You need to try to perhaps do something a little bit different. Okay, so what we're going to do is take a slightly different track. Again, we're going to assume that we are after a regularizer that's differentiable. So we then have this optimization problem that we want to solve, and if R is differentiable, we can actually write down a closed form expression for the solution. So you might say, okay, could I somehow represent the solution to this using a neural network where I've got some components of it that I need to learn? So what we know is that if we had a linear operator A, then we can, well, okay, sorry. First of all, I've got this big giant operator inverse in here, right? And it's not really clear how you would directly represent that with a neural network. And that's where the Neumann series comes in. So if I had a linear operator A, then I could write the inverse of I minus A just using this simple power series expansion or Neumann series expansion. And in particular, if this operator A is contractive, then we know that the higher order terms are smaller, and that just using a few terms in this expansion is going to be a reasonable approximation to this inverse that we're after. So what we're going to do is we're going to try to combine these two things. We're going to say, all right, can we somehow use a Neumann series expansion in this solution that we're after, and then try to learn the best way to regularize inverse problems. Okay, so everything with the Neumann series is based on linear operators. I'm ultimately interested in nonlinear regularizers, so there's a little bit of cognitive dissonance here. But just suspend disbelief for a couple of minutes, and we're going to come back to that issue in a little bit. Okay, so here's the basic idea. We start with this closed form expression that I described before. I plug in this Neumann series expansion, but I truncate it with just B blocks. And I can write this sort of with a nice block diagram like I have here. So what I'm doing is I am taking my current estimate, and I feed it into a part here that's going to take into account my operator or the inverse problem that I care about. And in parallel, I feed my current estimate into something that computes the gradient of my regularization function, and then I add them up. But now, what's coming out of these individual blocks are not my individual estimates. But because I have a Neumann series, I'm going to have to add together the output of all of these different blocks to get my final estimate here. Yeah, Albert.
I'm uncomfortable with this formula grad. So R is a general differentiable function. So when you write this second line, grad R is at what point? Sorry, grad R is not a fixed operator. X is a fixed operator. What does this formula mean? This formula looks like beta hat depends linearly on Y. There must be a catch here.
It's linear. I mean, R is quadratic.
So R is quadratic, or R is R of beta is differentiable.
Right. So basically,
so
here's
quadratic. I agree with all this. I don't understand what this formula means if R is not quadratic.
right. So I'm completely with you. So basically, this equality, or well, modulo the truncation, right? Going from here to here makes complete sense if the gradient of R is linear or if R itself is quadratic. So now what we're going to do is we're going to start with this equation here and replace the gradient of R with something nonlinear. So in general, by doing that, I mean, I can just do it, but now it's no longer approximately equal to the thing that I care about. I've gone away from my original goal. And that's the thing that I'm going to talk more about a little bit later, like why or when does this even make sense, or how do we think about this? But right now, what I just want to say is that what the Neumann network is doing is it is computing this last line where I've replaced the gradient of R with a neural network that I'm going to learn from data. Now, so that's just, it is what it is, and then we'll talk a little bit later about when or why that might make sense. But one thing that I want to point out that is in contrast to what we saw with the gradient descent network that we looked at a couple of slides ago is that I do have these red lines that are kind of pulling out the output from each one of these blocks and adding them all up. And these are somewhat reminiscent of something called skip connections that have appeared elsewhere in the neural network literature. So things like res nets or dense nets they all have these skip connections. And they were derived perhaps from more solid engineering than necessarily mathematical principles. But we're seeing the exact same kinds of structures show up in these Neumann networks, whereas they were not present when we did things like gradient descent networks. And we think this is part of why we're seeing some improvements when we start using these Neumann network architectures, and I'll talk more about that in a little bit. So before I get into properties of these networks, I just wanted to show you a couple of experimental results. But are there any questions so far? No? Okay. Okay, so let's look at a couple of experimental results. So we did comparisons with a bunch of different things. We looked at some, let's call them classical methods, like using sparsity regularization. We tried to use these GAN-based approaches where we do all of our training in a way that's agnostic or decoupled from our inverse problem at hand. We also used a residual autoencoder, which uses this model X in the input, but otherwise has no knowledge of the operator X at all. And then we looked at unrolled gradient descent and these Neumann networks. And one thing I want to mention, and I think is interesting about this general setup, is that you can think about this whole block diagram as being one giant neural network, if you will, where some of the connections are learned. They correspond to the things we're learning about the regularizer, and some of them are fixed and determined by our forward model X. So one way of thinking about this is that we're using the underlying physics of the problem or of our observations to somehow constrain the architecture of the neural network that we're using to solve this problem. Okay, so we tried this out on a number of different training data sets for a number of different inverse problems, and I'm just going to show a few quick examples. So here's a deblurring example where the first column has the original and then X transpose times our observation Y. Then we get the result of the Neumann network and the residual of that result, so where our errors are. What we get with the gradient descent approach or with a residual autoencoder. And similarly, we've got results for compressed sensing. And the results that I am not showing, so I mentioned a couple of other methods, they're doing so much worse that it wasn't worth showing them here. But what you can see is that we are getting some advantages from using this Neumann network architecture. So I've got a big table where the Neumann network, and N here, is consistently doing well for a range of different inverse problems and for a range of different training data sets. Now, one thing I talked about at the beginning was this notion of sample complexity. Like, how many different training images do we really need to be able to accurately learn how to solve these inverse problems? And so we actually did these studies for a range of different training data sizes. So we looked at 2,000 training samples, 30,000, 50,000. And what we're seeing is that the PSNR, or the accuracy of Neumann networks, is better across the board. But, sorry, my legend's covering up part of my bar. But we can see that some of these other methods really, really struggle when you've got small sample sizes. Okay, one other kind of nice feature of these approaches that I wanted to mention, we can do some preconditioning. So starting from this nice mathematical framework allows us to think about ways to even improve it and do it, make it perform better. So this is the Neumann network that I showed you before, where our initial input was simply X transpose times Y. So we have to just fully learn a regularizer. But you might think that a good regularizer might consist of a linear part that we could maybe guess ahead of time, plus some other part that we need to learn from data. And so what we did is we tried to combine, what we know about Tikhonov regularization with these Neumann networks to improve the performance. So in particular, instead of inputting X transpose Y, we set things up so that we could actually input the Tikhonov estimate. And then we had to be very careful about what we actually had in these top blocks of the Neumann network to account for the fact that we're inputting this Tikhonov estimate, but it actually gives us something that performs significantly better. So this is sort of the revised preconditioned structure where we've got a new input and new top blocks, but the overall architecture is still very similar. And what we see is that across the board, the preconditioned Neumann network gives us much better peak signal-to-noise ratio numbers and smaller residuals for problems like deblurring. Okay, so let me tell you a little bit about some of the more theoretical work that we did and address essentially the question that Albert raised, like, well, what are you doing by replacing something that needs to be linear with something that's nonlinear? So, and more specifically, we started with this Neumann series expansion, but if A is a nonlinear operator, which once we start putting neural networks in here, it must be, then this series expansion that underlies our whole architecture is no longer true or valid. And so what can we say about whatever this thing is that we're working with? Can we somehow justify this architecture? So we studied this in the context of a union of subspaces. So we're going to assume that all of the images that we care about lie on a union of subspaces. And this is a model that's been considered before, so such as with the Yale face data set, right? People said, oh, you know, you could imagine each person's face is lying on a subspace, but depending on the lighting conditions, they might be in different places in that subspace. Okay, so we're going to assume that all of our training samples, all the samples that we care about, lie on some unknown union of subspaces. And what we want to do is, in that setting, understand what this Neumann network estimator is doing. So our estimate beta hat corresponds to this expansion, where capital R is the gradient of our regularizer. It's the thing that we learned. And we motivated this from the perspective of a regularized least squares estimator, but it's not necessarily clear that that's what we're computing. Okay, so the question is, what can we say about this estimator in the specific case of a union of subspaces? All right, so we've got two results, one which builds on the other. So first of all, what we show is that in this setting, you can actually write down an optimal oracle regularizer, or regularizer gradient, capital R, and that gradient is piecewise linear in beta. So basically what happens is if you were to input, the ideal thing you'd like to do to recover beta is to figure out which subspace beta came from, and then do least squares on that subspace, right? So based on that intuition, you could actually write down what regularizer you would hope you would learn. And so we wrote down what that is, and then that regularizer R. And then what we showed is that you can actually express that regularization through this Neumann network architecture. So there is a set of weights in this Neumann network architecture that corresponds to this ideal oracle optimal estimator. In addition, what we can show is that if you look at what's coming out of each of the blocks in this Neumann network, let me go back to my block diagram here. Here. Okay, I've got the output of this block and the output of that block, etc. If I look at the output of each one of these blocks, they all are kind of closest to the same subspace. So even though all of my training data is in this union of subspaces, for any given or any particular sample, when I feed it through this network, everything is operating as if I just had one single subspace, and I'm operating in a linear regime. So even though overall my operator is nonlinear, for any input that I would feed in from this union of subspaces, it behaves like a nice linear, well, the regularizer's gradient is linear, or it behaves like a quadratic regularizer. And not only that, but the ideal one. And so from that, those thoughts and those ideas, what we can show is that when we try to train this, I'm sorry, it's possible to find a Neumann network architecture where the distance between our estimate coming out of it and the truth can be made arbitrarily close to each other, where the closeness depends on the norm of the true data. but also on our step size eta and the number of blocks B. So as long as we're in this union of subspaces setting, we can actually well approximate, or we can get arbitrarily close to the true image that we're trying to reconstruct. Okay, so now does this really kind of bear out in practice? And so we tried it out. We said, let's actually generate some synthetic data from a union of subspaces, and then consider an inverse problem where our operator x is only going to measure the first 5 elements of the vector and miss seeing the last 5 elements. And then we tried to feed training data of this kind into our Neumann network and learn it. And we see a few things. First of all, what we see is that all outputs of all the different blocks are closest to the same subspace, just like the theory predicted. We also see that what this regularizer is doing is it's only operating on the null space of x, which again, from the beginning, we said it was kind of a desirable property, corresponds to learning these conditional densities. In addition, when we look at the learned regularizer gradient R, we said ideally it should be piecewise linear, where each one of these pieces corresponds to a different subspace in our union of subspaces. And when we test that empirically, we see that that's essentially what's happening. So when I choose any 2 points in a single subspace, then the operator is behaving like a linear operator on those. But if I choose points from different subspaces or points that are just somehow randomly selected away from my image manifold, then it no longer behaves like a linear operator. So it's only kind of linear where it's supposed to be linear, again, as the theory predicts. Okay, so I know I need to finish up here because I'd like my cocktail. But there's this question of, well, why do Neumann networks give us this performance boost, and what's really happening? So one thing that we also did is we said, can we somehow understand something about how we are training these Neumann networks? So we have to do some stochastic gradient descent and optimization to find our learned set of weights. And our hypothesis is that the Neumann network architecture with those red skip connections is actually making that optimization landscape a little bit friendlier or easier to navigate with stochastic gradient descent. So what we see is that if we look at the optimization landscape of the Neumann network, in contrast to what we get with the gradient descent network, we get a much wider local minimum. So it's much easier to kind of hone in on a good set of weights using these networks. Now this is a little bit more hand wavy, but what we do also see empirically is that as we train these things, the Neumann network kind of very quickly gets to a place where the log training loss is small, whereas the gradient descent network, which is also trying to learn a gradient of a regularizer, has to muck around for a while longer before it can hone in on a good estimate. Okay, so to wrap up, I just want to emphasize that in general, I think this idea of trying to incorporate your physical model or your inverse problem at hand in learning to solve inverse problems is pretty critical. And that these decoupled approaches make a lot of sense when you have mountains and mountains of training data, but in settings where you don't, such as medical imaging, it's a pretty essential ingredient. And these Neumann networks, along with things like unrolled gradient descent, have some really nice properties when you think about what's happening on a union of subspaces. But we think we're getting some additional benefits with this Neumann architecture due to the friendlier optimization landscape. And so I think that among these different stages of enlightenment, the next one is trying to use additional theory for solving, or from operator theory, for instance, to improve upon these ideas and develop even better architectures for solving these inverse problems. And we have posted this paper describing this in a little bit more detail on arXiv, so you're welcome to take a look at that. But in the meantime, I'm happy to answer any questions.
So thank you for the presentation. So if I understood well, at the end, you started by saying, okay, in the linear case, we have this Neumann extension, and then I somehow replace the identity by the gradient of R, and then you found that when you have a model which is a union of subspace, somehow this gradient is kind of linear, so it's okay,
right?
And somehow it makes sense to say that it's a good approximation. But I guess that more generally, the question remains. And so my question is, have you considered just considering another kind of algorithm which is designed to solve inverse problems, where the regularizer is not quadratic? I think in particular to the following fact. When R is a square norm, this Neumann expansion just corresponds to early stopping. It's the Landweber regularization scheme. And there is an extension of the Landweber iteration scheme for general regularizer, where you can use mirror descent. And this algorithm has a couple of steps. One step which use the matrix X, another step using not the gradient of R, but the gradient of the Fanchet conjugate. And so you could just copy-paste that and put that on your neural network, and maybe in that here, trying to learn not the gradient of R, but the gradient of its Fanchet conjugate. Does it make sense?
Yes, it totally makes sense. I think there's a lot of great nuggets in there. So first of all, yes, trying to decide what your learned neural network should represent, it's not clear, right? We're having it represent the gradient of R. Other people have had it represent some sort of proximal operator, which is a different beast, and then you're talking about this fractional conjugate operator. And I don't really have a good sense of exactly what the trade-offs are there in terms of just, I don't know, representation theory, I guess. But another thing that you're kind of hinting at is that there are methods that we know of for handling nonlinearities in systems of equations. And could we somehow incorporate those directly as opposed to, you know, ad hocly adopt or morphing something that was designed for linear operators? And that is something that we've thought about. So for instance, there are methods for solving nonlinear PDEs. So could we somehow use those ideas to come up with an alternative scheme? And then have some theory that goes along with it beyond just a union of subspaces. I think that's a really promising and interesting direction. But well, I mean, the honest truth is we tried it out and we had a hard time with the training. So is it because we just didn't, you know, pose things well enough and that there's some alternative architecture? Or is it that once you start including, like doing this formally and incorporating Jacobians and everything else, that the optimization landscape just fundamentally becomes much, much harder to navigate? I'm not really sure what's going on there. But what I would say is that it is nice in classical convex optimization to be able to say something about convergence and to say something about how my error depends on how many different iterations or blocks that I have. So if we do any kind of optimization, whether it's proximal gradient or gradient descent or mirror descent or what have you, and then truncate it, then and use a nonlinear regularizer, then I think it's pretty hard to say what's going to happen there. And that's why I think trying to think about, you know, methods like based on solving nonlinear PDEs, where we might be able to say something more concrete about these truncations in nonlinear settings, is especially interesting. But like I said, I don't know how to do it yet. Yeah.
Okay, thanks.
Thank you for your talk. So you had the hyperplanes and you had the manifold as an example of sets where you have good images in them, and images which lie outside are some sort of bad images. Okay, but now what's with the if you go from a good image to a bad image, like on some sort of curve or so, and at some point you leave the manifold or so, and I mean at this point you basically change only one pixel in the entire image, and you say, oh yeah, I was at a good pixel, but now I'm at a bad, I was at a good image, but now I'm at a bad image. And I mean, this feels a little bit unnatural. Or to put it the other way around, I'm thinking that maybe a manifold or so is not the right way to say, to separate the images, the good images from the bad images or so, because it's more like, yeah, right. It's okay, it's not okay, but it's a bad image.
Okay, so when we think about methods like these GAN approaches, where the regularizer really is yes or no, it's either good or bad, then I agree it's very harsh. Maybe not terrible. I mean, if we're looking at people's faces and there's a big red pixel in the middle of the eye, maybe we really do want to say that that's not on the manifold that we care about. So I wouldn't explicitly say that that's definitely the wrong thing to do. Now, that said, you could imagine for the union of subspaces stuff saying something a little bit gentler, like somehow I want my regularizer to promote things that are closer to the union of subspaces. And in fact, this ideal regularizer that I was mentioning, I think was operating more along those lines. So it was a softer kind of regularizer than I described with the GAN approach. And so, yeah, and you know, I mean, this Neumann network seems to be working well on real data that is not exactly on a union of subspaces, right? We might think about it as lying on some sort of smooth manifold that we are simply kind of approximating with a union of subspaces, and that's okay. But I think the fact that it's working reasonably well on real data suggests that it's not quite as harsh and bad as you're worried about.
Thank you.
Just to continue along the line of this question. So typically what you showed is the case of where basically you have a sparse vector and then your network is estimating the support and then you invert in a matrix, the gram of the matrix, restrict it to the support, and everything becomes linear. Have you tried the same thing if you replace the vector by a matrix, which is low rank, which is the typical thing where the manifold is not linear?
I'm sorry, what's the sparse vector or the low rank matrix?
The beta that you were showing.
Like beta, yeah.
The beta, so the network estimated the whole support outside what the part that you removed, right? That you inpainted in your slide.
You want to go back to one of these
yes.
block diagrams, maybe?
In the example that he showed, not here.
No, not here.
Not here. A little bit. I don't know the result. At some point, you showed an example with a very simple vector, 1D vector.
Oh, yes, right.
Yeah, this one. Yeah,
okay.
Absolutely. Yeah. So for this one, so this is your ground truth, and then you mask the part of it, and then it was able to estimate the rest, right?
Right.
So here, everything, the structure is linear. This is what I mean. So he only has to estimate.
The inverse problem X is linear.
Yeah,
that is totally right.
Yeah, but the structure of the vector itself is linear. If you replace the vector here with the matrix, and what you know is that basically you mask the matrix, and you know that the matrix is low rank. So you have to estimate both the singular vector, the singular values, and singular vector.
Right.
So it's not really in union of subspaces, right?
Yeah.
It's a union of manifolds, which is completely linear. Have you tried this?
No, we haven't tried that. I think it's an interesting question, but no, we haven't thought about that. Well, I mean, I guess what we know is that since we're using ReLU networks, we are going to get something out of this network that is piecewise linear. And so we said, well, when does piecewise linear really make sense? Well, certainly it makes sense in this union of subspaces setting. You could imagine it making sense in other settings, like this low rank structure that you're describing. I think it could work, but yeah, that's pretty speculative. I'd have to think about it more, but it's a really interesting question.
Thanks.
Yeah.
Any other question? Yes?
When you were talking about learning prior in different steps, and when you showed that the process is gradient descent and then denoising, gradient descent and denoising, do you think that we can go a little farther and include one step which may be a kind of segmentation of the image, and then different denoising depending on the context on the segmentation. So right. This has some relation with the hierarchical model, prior model, with some hidden variables, right. Where this hidden variable can be, for example, exactly the labels of the different segments. And this may brings us to a structure which is a neural network which gives first segmentation, and for each class of each label of the pixels, we can have another denoising process.
Right. So when we did our experiments, we did, we were really focused on somehow this wrapper, like this overarching architecture. And we didn't really muck around a lot with the architecture of the individual neural networks representing the regularizer. And it's possible that you could improve upon that. So we used a UNet, which has been well studied and performs very well in state-of-the-art benchmark tests. But our focus wasn't really on every tweak we could possibly think of, or post-processing, or whatever else, in order to just get good PSNR values. We were really trying to focus on trying to understand some of these trade-offs. So yeah, the answer is no, we did not do that. I wouldn't say that it's a bad idea. It's just that it wasn't really kind of what we were focused on. But that said, I think you're touching on something that's also super interesting, right? What we have in a lot of these settings is a wealth of training data and some sort of a physical model, either a physical model that describes our observation degradation, or perhaps even a physical model that says something about segmentation or other geometric structure. And trying to think about the best way to somehow marry the training data and our models is something that I've seen tons of different sort of approaches, but I don't really understand those trade-offs, and I think there are a lot of good open questions in that realm. Okay. Well, I'm happy to talk more over cocktails.
Okay, so thank you again.
Thank you.